Good evening. Today our guest is Martin Solar. Martin did his bachelor in Andrés Bello University in Chile, Santiago. Then he moved to Valparaiso, Universidad de Valparaiso, worked with Michel Touré on the massive stars, and postacally Patwin.
Rotation of
massive stars. And now he's a PhD student in Poznań and worked with Michał Mickiewicz on the host galaxy of the supernovae. Floor is yours.
Okay, thank you. So yeah, now I move to a different topic. It's called supernovae. These are basically massive stars exploding as supernovae. And here I'm going to show the star formation efficiencies for these locations of corpuscular supernovae. So let's get started with a representation of our Milky Way, which is a spiral spiral galaxy, and it's composed of really complex structure. For example, the bulge that is in the middle, the spiral, the interact, the disk, the halo, the dark matter that I'm not going to talk about, the stars, everything that is between stars, the interstellar medium, which that's the thing that I want to focus here, the interstellar medium. Basically the interaction between matter and radiation given by gas, dust, and cosmic rays. So this is our location in the here for the sun. It's our location, the solar system, which is located 8 kiloparsecs from the galactic center. So if we take into account all the supernovae that were discovered in our Milky Way, these are only 5. And we can see all of this. By the way, a supernova that was discovered, it means that was simultaneously observed by different civilizations and recorded somewhere. So basically, the coordinates that we have on the sky were translated to these 5. A lot of interesting can be said from this figure. For example, is that the Kepler supernova exploded 400 years ago, and the astronomical telescope was invented 5 years after this supernova. So even the new modern instruments are not able to discover more supernovae, but actually, as you can see, all of them are nearby, known at distances like 10 kiloparsecs, and a few kiloparsecs. So what is happening? Maybe we need to improve the stellar evolution models because it is expected from around 2 to 4 supernovae explode in our Milky Way per century. So if we take during the last millennium, that's 1,000 years ago, around 20 or 40 supernovae should be exploded in our Milky Way, but we only observe 5 out of 40 or 20. So maybe we need more data, or maybe to improve the stellar evolution model in our Milky Way. My favorite explanation, I would say the favorite from, thank you, the favorite from, and the community agrees, is that as we are located in the galactic disk, dust is playing a really important role in obscuring all the supernovae. Actually, all the optical light, I would say that for supernovae exploding here will not be possible to observe even with the most modern telescope or instruments. So what I want to focus in this talk is that supernovae are exploding somewhere within galaxies, and this somewhere, these are preferred locations, these are the giant molecular clouds and the star forming region or the H2 regions. So this is the baryonic cycle, let's say for a typical star-forming nebula, in which this is the place where stars are formed. And a star like our sun eventually formed here and evolved as a red giant, expand as a planetary nebula, and leave a white dwarf in the center. Unfortunately, I'm not going to focus in low mass stars, but massive stars. So a massive star is everything considered with an initial mass higher than 8 solar masses. And these stars eventually will evolve as a red supergiant and explode as a corpuscular supernova. We should say corpuscular. leaving or a compact remnant as a black hole or a neutron star, maybe sometimes nothing. And this explosion will contaminate with heavy elements the interstellar medium and will inject feedback, momentum, and this will affect the new generations of stars. So here, our idea is to understand how massive stars form, how they evolve, and how they explode. So I guess the best way to start defining this is with the explosion, how these stars explode. And this is from, you can see from the title, core collapse supernovae. So here you have the core collapse supernova zoom, in which in the top panel, you have the photometric evolution for the explosion of a star. Basically, the explosion expands, and it's given by the photometry. It at some moment will reach the maximum light in the optical and will decay. The idea here is to classify supernovae spectroscopically, and in that way we can understand the features, the observable features of these explosions. Basically, the idea is to constrain the features of hydrogen, helium, silicon lines, and define to do all the classification of supernovae. What I want to do is to constrain the progenitor stars that give that all the observable features are given by different progenitor stars. And all these features depends mainly in the initial mass, because we know from our stellar astrophysics courses that the most important parameter in order to model the evolution of stars is the initial mass. Also, we have the rotation, because stars rotate and that affects the evolution of a star. We also have the metallicity, which is all the elements in atomic number higher than 2, and mass loss, because stars also lose some mass. Actually, the rotation, metallicity, and mass loss are linked. So this is a non-linear model. The thing is that this are for single stars. Now, if we have a companion, it's called a binary interaction when two stars interact, and this is actually complicates everything, because now it's let's say a super non-linear model. So this is like the structure of a star before the explosion, like prior to the explosion, before the bang. And this is the so-called onion shell structured progenitor. The elements are distributed by layers. You can see the heavier elements like iron are concentrated in the core. But the lighter ones, like for example, hydrogen, helium, carbon, and oxygen, are distributed on the layers. So I would say that a more friendly representation is given by this cartoon, where we have a type 2 supernova, which the star, prior to the explosion, preserves the outer layers of hydrogen or helium. Well, in the community, it's called type 2 supernova, but I prefer to call this hydrogen-rich supernova, because it makes sense, because in the spectrum we observe the hydrogen features. On the other case, we have strip envelope supernovae, in which the outer layers of hydrogen were removed prior to the explosion. Type 1b, and a case that is even more extreme are the type 1c, in which the outer layers by hydrogen and helium were removed. So it makes sense, this name, this strip envelope. Now the idea is to see how these massive stars evolve. And again, this will be single and binaries. What I want to focus here is that the most massive stars are going to strip the outer layers because of the mass loss, or the rotation, or the stellar winds. But that's as I said at the few slides ago, that depends on the initial mass. But for stars with lower masses, with initial masses lower than 20 solar masses, a companion could be the main mechanism responsible to strip away the outer layers. So here we have the famous Hertzsprung-Russell diagram, in which in the y-axis we have the luminosity, and in the x-axis the effective temperature and the surface for stars. And again, I'm not going to focus the low mass regime, but for stars that are considered massive stars. Here we have the lifetime as a function of the initial mass for the dark region, that is everything within initial masses 8 and 100 solar masses. As you can see, the time scales span between 3 millions of years and 50 millions of years. And let's say that in the context of astronomy, so in the context of the universe, I would say are really short time scales. Actually, the dinosaurs went extinct 66 millions of years ago. And now we have the histogram, the same here by this dashed white line for single stars, how they expand their lifetimes, the time after the stars. So that's something between 3 and 50 millions of years. But what if we take, sorry, I forgot to say that this is weighted by the initial mass function. But what if we take into account the binarity function, that stars are expected to interact somehow? I will explain all the details of this later. But basically, I want to focus if we include binaries for massive stars, there will be an extended tail that will reach 200 millions of years, and it's a significant change. So now the idea is to talk how these massive stars form. And these are within the giant molecular cloud, which is the place where stars are formed after gravitational collapse. Which, by the way, there is expected to have some association with the more massive stars. Yes. So here we have a face-on representation of one of my favorite galaxies, NGC 628, in which it is color-coded by CO, and CO is basically the carbon monoxide, and the molecule of carbon monoxide is a tracer of the whole molecular gas, the place where stars are formed. And also by the orange, we have H alpha. H alpha is a tracer or a proxy of the warm ionized. We can say that on average, statistically speaking, these two regions are overlapping. This is also known as the Koenig-Schmidt law at giant molecular cloud scales. I will go into that later. But here we have a cartoon representation of a giant molecular cloud. And something that I really want to highlight is that this giant molecular cloud have typical sizes of 100 parsecs. And actually, we use this resolution. I will explain this later. Because this is the place where stars are formed and evolved. So the typical lifetime after gravitational collapse and form of the first stars, the lifetimes of this giant molecular cloud is around 16 mega years, with some error bars, but I forgot to include it. So now we have already an idea how these massive stars form, how they evolve, and how they explode. So coming back again to the title, how it's possible to combine everything we did. All of this is with the star formation efficiency in calculus supernovae. And we will use one technique called integral Phillips spectroscopy, in which you see that there is like a grid for the carbon monoxide and H alpha, and each of these frames, let's say, it contains information about spectrum, could be optical or radio. So we use one of the two best telescopes nowadays. First, VLT Muse, which, well, I'm not going to give all the technical details. You can ask me at the end. But Muse, located in the VLT, covers the optical range. And this optical range, the parameters of the, let's say, observables that I want to focus in this talk is H alpha, H beta, O3, and H2. And these are tracers of the warm ionized gas. On the other hand, we have ALMA covering only the millimeter range using this molecule, the carbon monoxide, is a proxy of the cold molecular hydrogen gas. And the only technical thing that I'm going to say is that they can reach similar resolution, 1R7. And this resolution in the local universe, with this resolution in the local universe, it's possible to constrain the giant molecular cloud sizes, or H2 regions. So here we have, like, let's say, a space-bound galaxy, in which is color-coded by H alpha, and the contours represent the carbon monoxide flags. So here we have like a supernova that exploded, so we can extract the environmental parameters, taking like the pixel position of some regions, and that way we can understand the progenitor channels from the supernova. The main parameters that I want to focus here is the molecular gas surface density driven by the sigma mole. We also have the star formation rate surface density given by the sigma SFR, and combining both parameters, it's possible to compute the star formation efficiency, or the molecular gas depletion time is basically the same. As a secondary parameters, we have the metallicity and the stellar age tracing. So the data, it's time to talk about the data. So my supervisor, before I arrived to this PhD, he started a survey called the ACOS survey. ACOS because ALMA carbon monoxide is CO, supernova survey, which basically locates ALMA observation, observing the carbon monoxide interstellar medium condition for a number of supernovae, strip envelope supernovae. A similar thing, but much more developed, is the Musin survey. It's the same, but using MUSE. We also made use of the other data sample, like for example, FANGS, archival data, which is basically data that is somewhere in the internet, plus our own MUSE observation that we got time 1 or 2 years ago. 2 years ago. Yes, that's enough. So using both telescopes, using spatial scales of 100 parsecs, we gather a total of 21 hydrogen-rich supernovae and 19 strip envelope supernovae. That's the most quantity of sample that is possible to get. Now going to the results, we have the empirical cumulative distribution function for 3 different samples. First, the host galaxies, basically the values of the pixels from which some of these supernovae exploded. We have in blue, divided dotted blue line, the hydrogen-rich supernovae, and for strip envelope supernova, the dashed red line. So basically, we see in very few words, we see that strip envelope supernovae are exploding in values of the star formation rate higher than in comparison with hydrogen-rich supernova. And this is in agreement with previous results, like for example, all of them that they use MUSE. So we are not finding nothing new. This is something this is not like a new thing. And all of this paper concluded that strip envelope supernovae should be associated with more massive stars. The progenitors should be associated with more massive stars in comparison with hydrogen-rich supernovae. But I would say there is one caveat here, is that we are only using one tracer, in this case, H alpha. So the idea here is to expand this uni-wavelength approach to, let's say, a multi-wavelength approach. That's why, in our case, we also include the molecular gas surface density. So basically, we see that hydrogen-rich supernovae and strip envelope supernovae are exploded in similar conditions, and that could be explained by this way, that they have similar lifetimes and they have similar initial masses. So basically what it means physically is that both populations of stars are being formed in similar condition of the molecular gas, and the cloud is dispersing in a similar way. Well, this is not in agreement with these two previous papers, but the main difference is that in Galvan in 2017, they used spatial scales comparing to galactic structure, that is 2 kiloparsecs. And 2 kiloparsec is not possible to resolve the giant molecular cloud. Also, in Mickiewicz in 2023, they actually measured, they used ALMA, but the difference is that they used a reduced sample of only 5 type 1c supernovae plus 2 plus 3 type 1b supernovae. That's why we did a study that was how to say this, was a study that was, our sample was a large sample statistically speaking, because we use simulations and observations, and simulation agreed with observation. So yeah, as I told you, previous studies already used the star formation rate, also the molecular gas surface density, but now the idea is to combine both. Here we have two independent variables, which I want to highlight here, that two independent variables are two variables that do not depend each other. Here we have the y-axis, the star formation rate surface density as a function of the molecular gas surface density. And this is also known as the star formation law that was first discovered by Martin Schmidt 60 years ago, and studied by Robert Kennicutt 30 years ago. And basically, and this is the most updated relation from the star formation law, where there is a huge scatter, but the relation stays, and the slope is 1. So there's like a perfect correlation. Basically, it says if there is more amount of gas, more stars are formed. We did the same using our host galaxy. It's in agreement with the literature. What is new is this plot in which we have the hydrogen-rich supernovae in the star forming law. And well, we see that the hydrogen-rich kind of follow the Kennicutt-Schmidt law, but they have higher values in the star formation list. So it is expected that the progenitor channels of these supernovae are associated with massive stars. What is more interesting is when we include strip envelope supernovae, driven by these red squares. So if we focus in the x-axis, they share similar properties. But if we focus in the y-axis, the strip envelope supernovae are associated with more massive stars. So here's what I want to focus. Here is where I want to focus. So we have the molecular gas surface density and the star formation rate surface density. And the ratio gives us the star formation efficiency. And the star formation efficiency is basically the rate at which stars are formed given an amount of gas. And this is in these units. Maybe it's more friendly to talk about the molecular gas depletion time, which is the inverse of the star formation efficiency, because it's in units of time. So now we have like this star forming law, but now it's possible to trace different lines for the depletion time, molecular gas depletion time, or the star formation efficiency. And we can see that hydrogen-rich supernovae, let's say, follow the trend of gas that is going to be consumed in 10 billions of years. And for the case of strip envelope supernovae, the gas is going to be consuming regions that stars are more efficiently forming, with depletion times of 1 billion of years. So yeah, this is like one way to see this. You see that the uncertainties do not agree. So I want to give one parenthesis. I will explain this later, but one parenthesis is that the more massive stars are expected to radiate the UV photons and ionize the surrounding media uh, to excite the atomic gas. And we see the spectrum in galaxies or H2 region. We see all these prominent lines. So something that I want to say before is that we don't use these three samples that are given by the cross, because this is something called the PPT diagram, which is an emission line diagnostic, where the ratios of the O3 and H beta and the ratios of N2 and H alpha tell us how the gas was ionized. Could be by massive stars, this star from the regions, could be an AGN, an active galactic nuclei, or could be linear galaxies. We only get rid of 3 data samples, which I didn't include before, but it's worth to say this. Something that I also want to say is that the giant molecular clouds are composed mainly of molecular hydrogen. And molecular hydrogen, it's it's a symmetric molecule. It's composed of hydrogen and hydrogen. And it's difficult, it's made almost impossible to excite at the typical temperature of giant molecular clouds, which they have how to say this, temperature of just few kelvins. That's why, and that's the most abundant molecule in the universe. The second most abundant molecule in the universe is the carbon monoxide, which is actually a tracer of these giant molecular clouds, as I said before. But there is a problem. As you can see, C and O are metals. So we need to correct our measurements by metallicity. Here we have that the metallicity as a function of the star's emission efficiency. And basically we see that both environments of the populations of both cortical supernovae are similar. So metallicity is not affecting our results. People always ask about metallicity, so it's not affected. Also, we have the stellar H tracer that is given by the equivalent width of H alpha. The equivalent width of H alpha is it measures basically how old or young is the stellar population associated to the region. We see that only a few regions are dominated by all stellar populations, but in general, all these comparing both populations of cortical supernovae, they're associated with stars with the same age. So we know that hydrogen-rich supernova progenitors, they have initial masses between 8 and 20 solar masses. But for strip envelope supernovae, if they have similar lifetimes than hydrogen-rich supernova progenitors, we can say that they have similar initial masses. If they have similar initial masses, the explanation to the progenitor channels of strip envelope supernovae are given by a binary system. Here we have an animation thanks to ISO for a binary system in which the star 1, the primary star, the more massive one, it had an initial mass of 20 solar masses. The secondary star, the companion, it had an initial mass of 15 solar masses. So eventually the primary star will evolve faster. It means it will expand first. And because of this expansion, the more massive star will donate, will donate mass to the less massive one. That's the reason how the progenitor star, the envelope is being stripped. And that's why we don't observe the hydrogen feature, or for some cases, helium features for strip envelopes. Yeah, here comes the explosion. So this is the evidence of binary model for strip envelope supernova progenitors, and here's my personal collection of all the studies that support the that strip envelope supernovae explode in a binary system. And yeah, this system will interact in somehow. So that could be the reason of why the strip envelope supernova progenitors are ionized in the hydrogen and helium, or even helium. So in this plot, which it is not, I didn't describe this. Well, it's not my plot, but you have these numbers represent the binary diffraction. So if we take into account 1, it means that all stars, massive stars, are going to be binaries. If it is 0, all stars are going to be single. So this is the ionized, how efficiently is the hydrogen being ionized. And if we take binaries as a function of time, it is going to be more efficiently ionized. Also, we have helium-1, in which if we take binaries, also the medium is going to be more efficiently ionized. So here, well, here it should say massive stars. Here it should say AGN. And strip stars are binary stars. So here we have like the evolution of the universe and the contribution, the relative contribution of the hydrogen-1 ionized photons. And in the early universe, let's say that 10% of this contribution came from binary system. And if we go to the local universe, that's basically redshift 0, 30% of the relative contribution is coming from binary stars. Also, we have in this plot the binary diffraction as a function of the age of 6 open clusters. We see that the binary diffraction, it decreases as a function of time. So maybe, just maybe, this is part of the discussion, strip envelope supernovae could be exploding in these young stellar clusters, open clusters. Also, we have like the radiation feedback as a function of time, which B represents binaries, S represents singles, and basically we see that this binary ionized, the radiation pressure is more efficient when we have binary systems. Also, we have the initial mass function, the IMF, which is basically an empirical relation, which for a given range of mass, it gives us the relative number of stars, and it decreases for the more massive one. What it's suggests, what could explain our results is that strip envelope supernovae are more efficiently, strip envelope supernova progenitors are more efficiently produced like in this part here with a alternative scenario with a higher upper mass cutoff, or could be maybe a flatter upper mass slope, or maybe what is proposed during the last years is that there's like a top-heavy initial mass function, and maybe our strip envelope supernovae are exploding are biased toward this top-heavy INF. This is one of my final slides. There's one more. Yes. This is not the periodical table that we learned from high school. This is the cosmological periodical table. And in each frame, let's say, there is like the astronomical mechanism from which each element, the contribution from each, how the element was produced. For example, or we will go to the simplest one, hydrogen. All the hydrogen was produced from the Big Bang. And most of the hydrogen helium came from the Big Bang and just a fraction from AGB stars and corpuscular supernovae. And you can see that most of these elements are produced in supernova in general. I want to focus here in three elements: oxygen, nitrogen, and carbon. You see that all oxygen is produced in corpuscular supernovae. A significant fraction of nitrogen, the most abundant element in our atmosphere, is produced in corpuscular supernovae, and also a significant fraction of corpuscular supernovae produce carbon. And carbon is the most important parameter for the origin of life. Actually, I forgot to put it somewhere here, but carbon it's enhanced in the production is enhanced for when you have a binary system and the binary system strip away the outer layers of the binary star. So maybe the carbon that came to our Earth could come from strip envelope supernova. Here we have the corpuscular supernova ratio for the local universe. And we see that one fifth, 20% of all corpuscular supernovae are hydrogen poor. But that's another way to call strip envelope supernova. So yeah, this is my final slide. This is the updated plot of the star formation efficiency, sorry, the star formation law or the Kennigan-Schmidt scaling relation. Yeah, very massive stars are more efficient. If I have to summarize this in one sentence, efficient star forming regions for massive interacting binary stars. So yeah, that's what I have to say. Thank you.
Question? Okay, Martin, I have the question. You mentioned that equivalent width of the HR is a tracer of H. How it works?
So yeah, we can go to this slide. So yeah, basically the equivalent width of H alpha it measured how the contribution of massive stars that gives basically it ionizes the it excites the H alpha, and that's dominated by massive stars. And the whole stellar population they contribute to the continuum. So basically it's a ratio, H alpha and the continuum. So H alpha is massive stars, continuum is all stellar population. If it is higher, it should be associated with young stellar population. If it is low, should be associated with all stellar population. And here we have this threshold, let's say when the equivalent width is lower than 6 angstrom, the region should be dominated by all stellar population. That's how it works.
It's like a region without gas and star forming when the equivalent width just drop. Yes.
Yes, it's a combination of the contribution of massive stars and all stellar population.
Okay, thanks.
That's what has been studied. I'm not the first who does this, so there are previous studies for this. This just was one extra study.
Okay, thanks. More question? Yes, please.
Excuse me, you have shown slide with this contribution of stripped envelope supernovae to ionization of medium or something, which is going increasing. Oh yes, this is yes, and it means that let's say 20% of supernovae contribute, say 70% to ionizing photons.
So this is not the supernova, but it's the progenitors.
Okay,
Strip star is stars that are
Wolf-Rayet or something.
also it will be massive stars. Here it says massive stars.
Mhm.
I don't know if you can read it.
Okay.
It says massive stars, and these are single stars.
Mhm.
Yeah, here I show it like this. So here are single stars, and these are all could be more fragile. The super star is a binary system, so how this binary system could ionize the medium could be due to a common envelope evolution. It's not the supernova itself, but the binary system
Okay.
contributing to ionize the gas.
Okay, so its importance is, let's say, increasing towards our time.
Yes. So I don't know if also the binarity fraction is increasing, but it's something that I should read also.
Okay.
Okay, more question? Okay. And we'll see the online question too. So if there is no question, let's thank our speaker again. Thank you. See you next month. Tam gdzieś leży.